Have you ever wondered why designing converters is so essential in the field of electronics? Converters, the unsung heroes in electronics, transform energy from one form to another. They enable devices like our smartphones, laptops, and electric cars to operate on direct current, even if the power supply is alternating current. Converters step in and translate this power into a form these devices can use. They ensure smooth operation of numerous electronic devices, acting as a bridge and efficient energy transfer. So let's delve deeper into the fascinating world of converters. Designing a converter is a complex process that involves several crucial steps. The journey begins with identifying the requirements. This is the bedrock of our design. We need to ask ourselves, what is the purpose of our converter? What type of power source will it be connected to? What will be the output power? How efficient does it need to be? The answers to these questions will guide us in the rest of the design process. Once we have a clear understanding of our requirements, we move on to choosing the appropriate topology. This step is like selecting the blueprint for our converter. The topology dictates the basic structure and operation of the converter. There are numerous topologies available, each with its own strengths and weaknesses. For example, some may prioritize efficiency, while others might focus on compactness or cost-effectiveness. Next, we dive into the heart of the converter, the components. This is where we select the specific parts that will make up our converter, such as the switches, capacitors, and inductors. Each component plays a critical role in the converter's operation and performance. Therefore, we must meticulously choose components that meet our requirements and work well together. Finally, we reach the exciting part, creating a prototype. This is when we bring our design to life and see it in action. We assemble the components according to our chosen topology and test the prototype to ensure it meets our requirements. This step is crucial as it allows us to identify and rectify any issues before the final production. Each of these steps is vital in ensuring the converter functions effectively and efficiently. The first step in designing a converter is to identify the requirements. It's a bit like going on a journey. Before you can map out your route, you need to know your destination. In this case, the destination is the specifications of the converter. These include input and output requirements, meaning what kind of energy or signal is going in and what needs to come out. Next, consider efficiency. Just as a car's MPG rating tells you how far it can travel on a gallon of gas, a converter's efficiency tells you how much of the input it can turn into useful output. The higher the efficiency, the less energy is wasted. Finally, safety standards. These are the seatbelts and airbags of your design, ensuring it operates safely under all conditions. Think about things like overvoltage protection, short-circuit protection, and thermal management. A clear understanding of these requirements is the foundation of a well-designed converter. Once the requirements are clear, the next step is to choose the appropriate topology. Now, you might be wondering, what exactly is a topology in this context? Well, in the world of electrical engineering, a topology describes the arrangement of components in a converter. It's like the blueprint of your project, which dictates how energy will flow through the converter. There's a wide array of topologies available, each with their own strengths and weaknesses. Let's delve into a few of the most common ones, shall we? First up, we have the buck converter. This is a step-down converter that is known for its efficiency and simplicity. It's great for applications that require a lower output voltage than the input voltage. Next, there's the boost converter. As the name suggests, it steps up the voltage. This topology is perfect for applications that need a higher output voltage than what's provided by the input. Then we have the buck boost converter, a versatile topology that can either step up or step down the voltage. It's a little more complex than the previous two, but its flexibility makes it a popular choice. While these are just a few examples, there are plenty more topologies out there, like the CUC, CPIC, and Zeta converters. Each of these has unique characteristics that make them suitable for specific applications. Choosing the right topology isn't just about picking one that meets your voltage requirements, though. It's also about considering factors like efficiency, cost, size, and complexity. The best topology for your converter will strike a balance between all these factors. Remember, there's no one-size-fits-all solution when it comes to converter topologies. It's all about understanding the needs of your specific application and making an informed decision. This might seem overwhelming, but don't worry, with a bit of research and some trial and error, you'll soon find the topology that's perfect for your converter. The right topology can make all the difference in the converter's performance. It's the backbone of your design, the foundation upon which everything else is built. So, take your time, explore your options, and choose wisely. It's an important step in designing a converter that not only meets your requirements, but also excels in its performance. With the topology selected, it's time to move on to choosing the components and creating a prototype. Selecting components is a bit like putting together a puzzle. Each piece must fit perfectly with the others to create the desired picture, in this case, an efficient and reliable converter. The components you choose must be compatible with the chosen topology and meet the converter's requirements. Let's break down the component selection process. First, you need to consider the voltage and current ratings of each component. These must align with the operational parameters of your converter. For instance, if your converter requires a high power output, you'll need components that can handle high current levels without overheating or failing. Next, consider the efficiency of the components. High-efficiency components often come with a higher price tag, but they can save money in the long run by reducing energy consumption and heat production. After selecting the components, it's time to create a prototype. This is where you bring your design to life. Prototyping involves assembling the components according to the chosen topology, essentially building a physical model of your converter. Now, the moment of truth. Testing the prototype. You need to ensure that it meets the specifications and performs as expected under different conditions. Testing involves applying various input voltages and loads and measuring the output to verify the converter's performance. Don't be discouraged if your prototype doesn't work perfectly the first time. It's common to face challenges here, and it's part of the process. Each test provides valuable data that can guide you in refining your design and making necessary adjustments. Remember, the goal is not just to build a converter, but to build the best converter possible. This takes time, patience, and a lot of testing. In conclusion, component selection and prototyping are two critical steps in designing a converter. These steps require meticulous attention to detail and a thorough understanding of the converter's requirements and the chosen topology. Selecting the right components and thoroughly testing the prototype are critical steps in designing a successful converter. Designing a converter may seem like a daunting task, but keeping a few key points in mind can make the process much smoother. Let's take a moment to reflect on these crucial aspects that we've discussed throughout the video. Firstly, understanding the requirements is paramount. A converter's design heavily relies on the specific needs it is intended to fulfill. Whether it's for a low-power application or a high-power industrial machine, the requirements dictate the design process. This step involves understanding the input and output voltage levels, the power capacity, and the operating environment. Next, we move on to choosing the right topology. This is where the technical aspect of converter design comes into play. Each topology, be it buck boost, or any other, has its own set of advantages and limitations. The key is to find the one that best fits your requirements and constraints. Once we have the topology, we need to select the compatible components. This involves choosing the right type of switch, inductor, capacitor, and controller. Each component plays a critical role in the overall performance of the converter, so the selection should be done carefully, considering factors like cost, size, and efficiency. Lastly, testing the prototype is a critical step. This is where we verify if our design meets the requirements and performs as expected. It's crucial to test under various conditions and make necessary adjustments. To wrap up, designing a converter is a complex process that requires a thorough understanding of the requirements, a strategic choice of topology, careful selection of components, and diligent testing of the prototype. But don't let the complexity discourage you. Instead, embrace it as a challenge and a learning experience. Remember, a well-designed converter is essential in powering the electronic world around us.